Hello and welcome to your lecture number 21 on moisture clouds, precipitation. This is for Earth Science. Glad you could be with me today. So we're going to be, again, going over latent heat, moisture clouds, precipitation, how basically weather, storms, and things like that form. So that's what we're going to cover today, and we'll get right on it. I hope that you are keeping along with your assigned reading there. So this is chapter number 19 in your book. And we're going to be covering lecture assignment number 21, so I hope you got that in front of you too, like I do. I got here on my other screen. So let's, without further ado, get into it. And I need my pen here. Now, first of all, like I said, we're doing moisture clouds, precipitation, so all that focuses on water. We need to understand water and the water molecule. Now, of course, you know water molecule is H2O. There's your H2O molecule down there. I'm sure you've seen pictures of that before. And, of course, you also know that H2O changes its phase, changes its state of matter here on Earth, right? You got three different states of matter. So you have solid, liquid, and gas. Now, solid, of course, we see solid water in nature as ice, right? Snow. We see liquid, of course, as rain. You know that. Now the gas you actually cannot see. So you cannot see with visible light, you cannot see or detect water vapor in the atmosphere. It's invisible. I put a picture here of fog just to kind of, again, help you visualize it. But really, you cannot see water vapor in the atmosphere. So a humid room will look the same as a dry room. You know, you can't tell. Of course, you can feel it when you walk into the room, but you can't tell with your eyes, okay? Now, one extremely important concept that we need to talk about here, and it's the number one question there on your lecture assignment, is what is latent heat? Now, latent heat is basically, you can think of it as the amount of energy that's stored in the bonds between water molecules. So as water changes its phase, that means it goes from one phase to the other, it's going to exchange different amounts of heat. We're going to talk about all exact details about how it changes heat and why and when. Okay. So first of all, let's know a little bit of terminology here. You know that when ice goes to the water phase, that's called melting. You all know that. Sometimes that's called fusion. It's another term for it. When water goes to the vapor phase, you know that's called evaporation. When water vapor goes to the water phase, that means that it goes from a gas to a liquid. Kind of think of like forming dew droplets or something like that. That's called condensation. And when you go from water to ice, of course, you know that's called freezing. All right. Now, every time that you go from one phase to the other, you're going to be either breaking or forming bonds. So H2O molecules are all stuck together with bonds. Okay, these are molecular bonds. We actually call them hydrogen bonds. And when you pull apart these bonds, it's going to either take energy, or when the bonds form, it's actually going to release energy. That energy is the latent heat. So you could imagine if you were the size of an atom, like let's say this was you right here, okay, and you were going to come over here and you wanted to pull this water molecule off from its neighbors, you know that's going to take energy to do that. It's going to take some exertion and force, okay? That's the latent heat that you're actually breaking. So it's kind of, you can think of the heat that's stored, or the energy that's stored in the bonds of the water molecules, okay? Okay, so H2O molecules, they change, they break, they reform as they change state. And it takes energy to break those bonds, and it releases that same amount of energy when they form, okay? So basically what I'm trying to outline for you here and show you is that when water goes from one state to the other, H2O goes from one state to the other, it's either going to make the environment hotter, or it's going to make the environment around it colder. So it's either going to absorb energy or release energy, okay? So for example, when water turns into steam, it's going to have to break all of these bonds that hold the water molecules together, okay? So that takes energy. So actually, I know this sounds ironic, or may not ironic, but paradoxical, But when water goes from liquid water to a gas, it evaporates, it's boiling or steaming, it actually takes energy to do that. So as it goes through that process, it's actually cooling the water down as it boils and as it evaporates, okay? So that's why, for example, when you boil a pot of water, it takes a long time to boil that water off. You know that, right? Like if you put a pot of water on the stove, it would take a long time to boil off all the water. It takes a lot of energy to break all those bonds, okay? That's latent heat. Same thing actually happens in reverse. When water melts, it takes energy to break the crystal ice bonds. So again, when water goes from solid phase to a liquid water phase, it's the same kind of thing. It's going to take energy to break those ice bonds and make water, okay? So I know it sounds ironic, but as ice melts, it's actually taking energy from the environment, okay? Another thing, the exact opposite happens with energy when you reverse the process. So let's talk about, you know that when you get hot, right, you start sweating. Okay, the reason that you sweat is it helps to cool us down because it takes off the heat of our body, and that's the latent heat of evaporation. It's actually removing the heat from our bodies when we sweat, right? And actually what's interesting is that the totally reverse process also happens. So I know this, again, sounds weird, but when water freezes, it actually releases energy. So instead of absorbing energy, it releases energy. And so that is why, for example, in California, where I'm from Orange County, California, we have a lot of oranges there. We used to have a lot of orange groves. The farmers, if there was going to be a cold snap and a freeze, the farmers would actually turn on all the sprinklers and irrigate and cover the fruit with water. And the reason is that when ice forms around the fruit, it actually warms it up. I know that sounds ironic and strange, but it's true. It actually warms up the fruit and it protects the fruit from freezing and falling off the tree. So actually when we have freezes here in Corpus Christi, I know people put blankets, and that's a good tactic, to protect sensitive plants. But you can also turn on the water and saturate your plants, give them a really good watering. That'll help to prevent the ground from freezing, and it'll help the plant from getting damaged from the cold. So anyway, all that stuff's latent heat. Some terms you might not know. Of course, you know melting and freezing and condensation, but there's also these other processes that happened as well called sublimation and deposition. Sublimation is when you go from a solid phase, directly to the to the gas phase without going to the liquid phase at all. Okay, so it just totally skips that. You may have seen sublimation before. For example, you might have seen this before. Like maybe you've seen this before. You take something out of the freezer, you can literally see like gas coming off of the cold thing from the freezer, right? So it's going directly from the I can say the solid phase to the vapor phase, okay? Vice versa. Now I know this doesn't happen very much in Corpus Christi, but maybe you've seen this. They used to call this old Jack Frost, right? Would come and make designs on your window. But really what's going on is that on really cold days in Corpus Christi, maybe on your windshield, you might see these little ice crystals that form. That forms from deposition, where water vapor goes directly from the gas phase to the ice crystal phase, okay? So those are just two terms you should know as well, because that comes up a little later bit in this lecture, okay? So, moving right along, we need to talk a little bit now about humidity. I know that you don't have any questions about this on your lecture assignment, but this is a very important thing that you need to understand, because we're going to talk about two different kinds of humidity, okay? So again, even though it's not on the lecture assignment, please humor me and listen to this, because you need to know this to understand the rest of the lecture. So first of all, you know that the air can have anywhere from 0 to 4% water vapor dissolved into it, right? I know it's kind of weird to think of water vapor being dissolved into air, but it's very similar to how it is, you know. So this term humidity, it's the amount of water that is in the air, okay? And there are two different ways that we think about humidity. There's something called specific humidity, and there's something that you're probably more familiar with called relative humidity. Usually when you listen to the weather report, like for example, if I were to go and pull up the weather, right? I'll go Corpus Christi, weather underground, and I want to check the weather. Of course, there's an excessive heat warning today, as always in summer in Corpus Christi. And I want to know the humidity, right? So if I go to the humidity, and it's going to give me humidity in terms, I'm trying to see where it is. Humidity, you'll notice it's a percentage. That's relative humidity. It's what we're going to see is it's the amount of water that the air contains versus how much it can hold, okay? So anyway, going back to our lecture, the specific humidity is different though. It's the actual amount of water that's dissolved in the air. So we express that in terms of grams of water vapor per kg of air, okay? Relative humidity is how much water is in there, the specific humidity, divided by how much it could actually hold and expressed as a percentage, okay? So when it's 100% humidity, that means the air is saturated. It cannot hold any more water vapor, and then it starts to basically precipitate out, right? So it starts to condense, and it starts to precipitate, okay? So this is a curve that shows you the amount of water vapor that can be dissolved into the air based on the temperature. Hot air can hold more water vapor than cold air. So take a look at this here. Let's say that it's wintertime in Corpus Christi and it's 50 degrees right here, okay? It's 50 degrees. How much water can fit and dissolve into the air? Right there, right? Okay, you can see that it's maybe, 8 grams per kg of air, okay? Not very much water. Versus up here, let's say it's 100 degrees in Corpus Christi, yuck. Okay, we go up here. And what you see is that now the air can hold something like 40 grams per kg of air. So that's 5 times more water in the atmosphere than when it was only 50 degrees, okay? So that's why it feels so much like yuckier and stickier and humid in the hot weather than it does in the cold weather, okay? It's because the air can hold a lot more moisture, all right? So anyway, when air reaches the dew point, it's going to start condensation. What is the dew point? The dew point is the temperature at which a parcel of air with a given specific humidity will start to condense, okay? So let's say that we have a specific humidity of 20 grams per kg, okay? The dew point is given by this graph. The dew point of that parcel of air with that given humidity is going to be, looks like 25 degrees Celsius, okay? Which would be about what? Be about 75 degrees Fahrenheit, okay? So anyway, fog occurs when moisture in the air reaches the dew point. It's when the air reaches the dew point. Versus dew forms, like dew on the grass when you wake up, or dew on your car in the morning, forms when the surface of your car or the surface of the grass or the surface reaches the dew point, but the air has not. When the air reaches the dew point, then that's when you get fog formation. By the way, if you've ever wondered what it feels like to be in a cloud, you've all been in a cloud before, okay? Fog is just a low-lying cloud. It's just a cloud that's on the ground. So there's nothing magical or mystical or wonderful about it. You've all been in a cloud before. It's just fog. Okay, it's just droplets of water that are so small they can't sink and fall to the ground. Okay, that's all a cloud is. That's all fog is. So what's the difference? For example, I say, like, what's the difference, number 6, between dew formation and from cloud formation? How are they similar? They're basically the same thing, right? Or I'm sorry, not dew formation. But dew forms when a surface reaches the dew point. Clouds or fog form when the air reaches the dew point. Okay, but you can see that they both involve something reaching the dew point, and condensation is occurring. All right. So moving right along here, I don't really like relative humidity. I don't really find it a very useful metric. It doesn't really tell you how humid it really is. And this is a good map to show that. If you look at the specific humidity global map, you'll see that the tropics are very humid, right? Versus up here in the North Pole and the South Pole, it's not very humid. There's not very much water vapor in the air. Why? Because the air is cold. It can't hold very much water vapor. Okay, so it has a low specific humidity. Vice versa, if you look at relative humidity, a world map of relative humidity, you would see that actually around the equator it's relatively low relative humidity, and in the poles it's a high relative humidity, and that doesn't make any sense because, well, of course it makes sense. It's true, but the air is saturated, has like 100% relative humidity in the polar and cold regions, just because it can't hold that much water vapor. Okay, whereas the equator, where it's very humid, has a relatively low relative humidity because it can just hold a lot of water vapor, so it's not saturated yet. Okay, so clouds form when a parcel of air reaches its dew point. Clouds form when the parcel of air reaches its dew point. The dew point is the temperature at which air with a given specific humidity is 100% saturated with water. Okay. All right, so here's a dew point map of the United States. I like dew points more than getting the relative humidity, because if the dew point is like 50 degrees, that means there's not much moisture in the air, so it's going to feel good, so if you want to know what a 50-degree dew point is, look at over here, like in the blue areas, like Utah or Idaho, Montana, Wyoming. That's like, it feels nice out, right? Whereas a 75-degree dew point, that's what like Corpus Christi feels like. This is in August, by the way. Okay, so where would you rather be, right? And you'd rather be in the Rockies in August versus Corpus Christi, right? Because it's not very humid and it's relatively cooler. But anyway, dew point, I like dew point more because it tells you actually how much water is really in the atmosphere at a given time. Okay, so anyway, you're going to see now that really the whole trick to forming condensation, to forming clouds, forming rain, precipitation, all this stuff, what's the trick? The trick is to get the air cold enough. It's to cool down the air. Okay. So how do clouds form? Clouds form when a parcel of air, when some air with given specific humidity reaches the dew point. All right. How do you get the air to cool down? I know that sounds like kind of a weird question. How do you get the air to cool down? Well, I'm going to tell you the way that you get the air to cool down. Has anyone ever seen one of these guys before? Right, you use it to clean your electronics, right? So if I go here, I can spray this, clean off my computer desk, and actually it needs kind of a spray right now. But anyway, let's say I spray this, and now I'm feeling this thing, and ooh, it's gotten really cold. It actually feels pretty good. It's July right now in Corpus Christi, so it actually feels nice to hold this. But anyway, it cools down when I spray this, right? Why does it cool down? Is it because the gas inside is cold? No, it's not cold. It's room temperature, right? What happens is that it's depressurized. When gas depressurizes, it cools down. So you've probably seen this before. You have an aerosol can, hairspray or something, or whatever, paint, like, spray paint, one of these things. when you spray it and you release the pressure inside, the gas cools down. By the way, it's the same principle and it's the way an air conditioner works. For those of you, maybe, I've had students before who are working, getting their certificates in like AC, maintenance, and they tell me that's how AC system works, right? Same principle is that when a gas gets depressurized, it cools down. And vice versa, when a gas gets pressurized, not depressurized, but pressurized and puts under pressure, it heats up, okay? So just to kind of demonstrate this to you right now, I actually did a little demo with a bike pump and a temperature probe, and I'm going to switch you over to that right now. So I'm going to go over to the lab and show you that right now, okay?
Hello everybody, and welcome to this little demo I'm going to do on adiabatic lapse rates. So you know that as a parcel of air rises through the atmosphere, it usually cools down, and that's due to adiabatic processes. So vice versa will happen as well. If a parcel of air sinks down, the pressure increases, air pressure increases, and you get adiabatic heating. So just to demonstrate these things, I have a little something here. I have a bike tube, and I have a bicycle pump, and I'm going to start inflating this bicycle tube with the bike pump, increasing the pressure inside of the bike tube. And I also have a little temperature probe that's hooked up there, and as you can see, you can read the temperature directly. Right now it's 21.7 degrees Celsius, and we're going to actually track the changes that happen to temperature due to pressure changes, right? So those are adiabatic heating, adiabatic cooling. So I'm going to pump this up and then depressurize it, and you're going to see how the temperature changes with those pressure changes, which are adiabatic processes. So I'm going to start pumping this up. It's going to take some time. I'm also going to start logging the temperature. So I'm going to turn this on, and then I'm going to speed up so that you don't watch me pump this up. It's going to go for about 3 minutes. So here we go. Okay, so I got this thing pumped up. You can see the temperature went up. And now what I'm going to do is I'm going to deflate this, and you're going to see the temperature start to drop once I deflate it. The temperature changes aren't very big because there are relatively small pressure changes that are going on. But anyway, you are going to see a temperature change. Okay, ready for the deflation? So there you have it. You can actually see the temperature climbing, goes up from like 21 point something to all the way up to 23, and then it starts to go down. So you can see in the graph how the temperature goes up and then goes down once I start deflating the bike tire. So anyway, that's an example of adiabatic heating and adiabatic cooling, and kind of models what would be going on as a parcel of air sinks and rises up through the atmosphere. So hope you enjoyed the demo.
All right, so welcome back. Hope you liked that demo. We're just moving along now with the rest of this. So as air rises now, think about what happens to pressure in the atmosphere. As you go up in elevation, the pressure decreases, right? So if you're a parcel of air and you start rising, your pressure is going to decrease. And what's going to happen to you? You're going to start to cool. You're going to start to cool off. We call that kind of cooling due to pressure changes, like I said in the demo, adiabatic temperature changes. Okay, adiabatic. Adiabatic, actually, it's kind of a weird word. It's a thermodynamic word. It actually means no energy change. It means it's a process that actually has no energy change. So even though the temperature is changing, it's not actually changing the overall energy of the system. So anyway, you don't really need to know that, but I'm just explaining where that weird word comes from, adiabatic. But adiabatic is the rate at which temperature is going to change due to pressure changes. Okay, it's the adiabatic cooling, adiabatic heating. Now, on Earth, if you're a parcel of air and you start to rise through the atmosphere, you're going to start to cool off adiabatically, okay? And the rate at which you cool off doesn't change. You're always going to cool off, with one exception, which I'm going to explain in a minute. you're always going to cool off at 10 degrees Celsius per 1,000 meters, okay? So let's say you start off at 10 degrees Celsius. You rise to 1,000 meters, okay? You're going to cool off 10 degrees Celsius. If you rise another 1,000 meters, you're going to cool off another 10 degrees Celsius. If you keep rising, you're going to cool off another 10 degrees Celsius. That's adiabatic temperature changes, and that's the adiabatic lapse rate. The adiabatic lapse rate, if it's dry, is 10 degrees Celsius per 1,000 meters, okay? So I say, number 8, what is an adiabatic lapse rate? You know that a lapse rate, we learned this in the last lecture, a lapse rate is the rate at which temperature changes through the atmosphere. A lapse rate is the rate at which temperature changes as you go through the atmosphere, okay? You go up through the atmosphere. Rate of change of temperature with elevation or with altitude, okay? The adiabatic lapse rate is the lapse rate, the change in temperature from adiabatic processes, from adiabatic cooling or heating, okay? It's the amount of temperature change due to depressurization or pressurization of a gas. All right, that's what an adiabatic lapse rate is. There are two kinds of adiabatic lapse rates. Two kinds. There's the Waller and the Dollar. And you have to know the difference in this class between the Waller and the Dollar. The Dollar is the dry adiabatic lapse rate, DALR. The dry adiabatic lapse rate. That is the lapse rate that occurs when there is no condensation. That's the lapse rate that occurs when there is no condensation. On the flip side, the wet adiabatic lapse rate, the Waller, okay, the Waller and the Dollar. The Waller is the wet adiabatic lapse rate. It is the rate of temperature change with altitude that happens when you have condensation. Okay, everyone, you know this already. I'm answering now number, what? Do we do number 9? What's the value of the wet adiabatic lapse rate? It's anywhere between 5 and 10 degrees Celsius per 1,000 meters. What's the value of the dry adiabatic lapse rate? 10 degrees Celsius per 1,000 meters. The wet adiabatic lapse rate is a range. It's between 5 and 10 per 1,000 meters. Why does the adiabatic lapse rate change when condensation begins? So when condensation begins, we switch from the dry adiabatic lapse rate to the wet adiabatic lapse rate. So let's say you're a parcel of air, you're rising. Okay, look at this diagram here. You're rising. You're going to cool off. See, this is temperature on the x-axis, altitude on the y-axis. So you're going to cool off at 10 degrees Celsius per 1,000 meters. Then notice that when condensation begins and you hit the dew point, that's the temperature at which a given parcel of air with a given specific humidity reaches the dew point. You're going to have condensation. Okay? You're going to have condensation, and then that's going to change the adiabatic lapse rate value. And it's going to change it to the wet adiabatic lapse rate value. And the reason that there's a difference says, why does the weight, oh no, sorry, number 11, number 12 says, okay, I guess I don't ask this, but why is there a difference between wet and dry? It's because of this. Are you ready for this? I asked this on the test, so get ready. Write this down, everyone. Put a little star next to it, because I actually asked this on the test. It's one of the possible short answer questions. Why is there a difference between the wet and the dry adiabatic lapse rate? And it's this. The wet adiabatic lapse rate, the rate of cooling, is offset by the release of latent heat of condensation. So as the water starts to condense, it releases latent heat, and that warms up the air while it's trying to cool adiabatically. So it offsets the cooling, and that lessens the rate of adiabatic of cooling. So that's why there's a difference between wet and dry adiabatic lapse rates. Okay. Now the reason, number 12 says, what's the difference between, number 11 says, why is there like a range of temperatures for wet adiabatic lapse rate between 5 and 10 degrees Celsius per 1,000 meters? It's because there's a range, there's variation in the humidity. If very humid air that's doing a lot of condensation will have something more like 5 degrees Celsius per 1,000 meters, whereas air that's almost bone dry is going to be more like the dry adiabatic lapse rate. It's going to be 10 degrees Celsius per 1,000 meters. Okay. So I know that that's clear as mud. It's the hardest concept, I think, in the whole class. So hopefully it makes some sense to you. But anyway, that's the density of cold air compared to hot air. You know that as air gets warmer, it's going to rise, right? As air gets colder, it's going to sink. So that's how you get air to rise, and that's how you get these adiabatic processes that are going to cool down and create precipitation. Okay, now we need to talk about these things. You see number 13, 14, 15, we're talking about stability, absolute instability, and conditional instability. So let's talk about some of these things. So we're going to see that the whole trick to getting precipitation to form is getting air to rise. Okay, we need to take a parcel of air and get it to rise. If we can get it to rise, then we can get the temperature to cool down adiabatically, hit the dew point, condensation will occur. Okay, so we'll talk more about that in the next lecture. But for right now, let's talk about atmospheric stability. Okay, so what the heck does stability mean? Stability is how much vertical movement there is in the air. So I want you to consider two scenarios. Let's say that you have a parcel of air and it starts to rise. Let's say that it's going over a mountain and it starts to rise. And as it rises, it cools down. But even though it cools down, it doesn't cool down enough to really become... So as it cools down, it's still colder than the air around it. So the parcel of air rises, it cools down, but it doesn't cool down, or I shouldn't say it doesn't cool down enough, but it cools down quickly enough that it remains colder than the air around it. Okay? Consider the opposite scenario. Let's say you have a parcel of air, and it's rising and it's cooling down, but the problem is that it's cooling down, but it's not cooling down fast enough. So that can happen with, for example, very humid air. The air is cooling down, but because of it's following the Waller, the wet adiabatic lapse rate, it's not cooling down fast enough. And so what happens is that even though it's cooling down, it always remains warmer than the air around it. Well, what does warm air like to do? It's not very dense, so it likes to rise. Okay, so in this scenario right here, where the air cools down but doesn't cool down fast enough, you're going to have unstable air. The air is going to have a tendency to rise. Okay, whereas in this scenario, the air always stays colder than the air around it, and then it's going to just basically hug the ground and stay at the ground level. Okay, so that's. So what you're going to see is that it's really important to know how the adiabatic lapse rate compares to the rate of change of the air around our parcel of air. Okay, so we call the rate of change of the air temperature kind of the environmental air temperature that a parcel of air is rising through. Okay, so we kind of like think of you had the parcel of air rising, right? But there's all this other air in the environment around it, okay? And it's getting maybe hotter or colder or doing whatever it does. But we call that rate of temperature change of the environmental air the environmental lapse rate, okay? The environmental lapse rate is different than the adiabatic lapse rate. A parcel of air, as it rises, is going to cool down according to one of the adiabatic lapse rates. It's going to cool down according to the dry adiabatic lapse rate. If it's not condensing, it's going to cool down according to the wet adiabatic lapse rate if it is condensing. But then totally separate from that is something called the environmental lapse rate. The environmental lapse rate is how fast the air is cooling down just in the environment, not including that parcel of air. Okay, it's just kind of like what the environment is doing on a particular day at a particular time in a particular place. Okay, and that just depends on weather conditions. So the environmental lapse rate, it just depends on what the particular time, place, weather of the day is. Okay, so there's 3 different kinds of lapse rates. Then there's environmental lapse rate. Let's say on average it's 6.5 degrees Celsius per 1,000 meters, but it can change. It could just be anything. I mean, because there's an average value for it, but it could just be anything. Sometimes it can get hotter as you go up in the atmosphere. Sometimes, like if there's a warm front, you can actually get hotter as you go up into the atmosphere. Okay, but totally separate from the environmental lapse rate are the adiabatic lapse rates, the dry adiabatic lapse rate and the wet adiabatic lapse rate. Okay. So that's how all those things are different. Now let's talk about number 13, 14, and 15, about absolute stability, absolute instability, and conditional instability. All right. You're a happy little parcel of air, and you start to rise. When you cool down, are you going to cool down according to the environmental lapse rate over here, or the adiabatic lapse rate? The answer to that is you are going to cool down according to the adiabatic lapse rates. Okay. So the environmental lapse rate just tells you what the air around you is doing on that particular day and how it's cooling off with temperature. Okay. But you're a parcel of air. You're going to cool off according to the adiabatic lapse rate, and you don't care what the environmental lapse rate is doing. You don't care. It makes no difference to you. It can cool off however it wants. The environment can cool off however it wants. It doesn't make any difference to you. You're a parcel of air. You're going to cool off according to the adiabatic lapse rate. You're going to do the dollar if you're dry. You're going to do the waller if you start to condense and you hit the dew point. All right. So you are going to follow. Now look at this. This graph is showing you temperature as a function of altitude. You're going to cool off according to the dollar. Oop. And then you hit the waller, and then you're going to cool off according to the waller. Okay? But notice that you're always colder than the environmental lapse rate. You're always to the left of the environmental lapse rate. That is absolute stability. That absolute stability occurs when the environmental lapse rate is less than the wet adiabatic lapse rate, which is always going to be less than the dry adiabatic lapse rate. Okay, so you're always going to be colder than the air around you in the conditions of absolute stability. Okay, absolute instability is the opposite. Okay, look at that. Now look at this. Now in this case, you can see that the environmental lapse rate, the purple line there, is now always to the left of the wet and dry adiabatic lapse rate. So that means that the air around you is always colder than the way that you're cooling off. So you're cooling off, and you're cooling off, you're just cooling off too slowly to match the environmental lapse rate. So that means that you're just going to start rising. There's going to be uncontrolled rising. There's going to be a huge amount of vertical movement of this air because it's going to start to rise and nothing will stop it. It will just keep rising. Okay, so absolute instability happens when the environmental lapse rate is greater than the dry adiabatic lapse rate. So the ELR is now greater than the DALR. Okay, parcel of air will thus warm faster than the surrounding air and thus be less dense and will drive buoyant vertical movement of the air. So this is when you've probably seen these like thunderclouds. They start rising up. They're like really towering tall, 30,000 foot tall clouds, right? That's absolute instability. Conditional instability happens when basically the ELR is between the waller and the dollar. Okay, it's when the ELR is maybe less than the dry adiabatic lapse rate, but more than the wet adiabatic lapse rate. So you end up with a crossover. So you see how here the ELR crosses paths with the adiabatic lapse rate. Okay, and that's conditional instability. All right, so when you have stable air, this is what it looks like. It's like nice stratus clouds, drizzly weather, That's stable air. It's not moving vertically. Okay, it's not going up or down. In unstable air, instability looks like this. You've probably seen this before. You get these big thunderclouds forming, right? That's when you get violent weather. You get cumulus clouds, thunderstorms, cyclones, hail, etc., etc., etc. Okay? So that's the kind of weather that you get from stable air and the kind that you get from unstable air. Okay? Stable air is gentle weather. Maybe at worst you get like drizzle. Okay? Unstable air is when you get all the scary weather, the storms, tornadoes, thunderclouds, blah, 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 hail, thunder, lightning, etc., etc. Okay? All right, number 17. Why does the outside of an ice-cold beverage get covered with condensation on a hot day? It's kind of a challenge question for you. I want you to think about it. I want you to think about, magic word here is dew point, so think about what all that means with the dew point. Try to use the dew point, word dew point in your answer, okay? But I want you to think about that. Number 18, let me talk a little bit about number 18. It says, why are condensation nuclei important for cloud formation? So one kind of interesting thing about when condensation occurs is that you can't go from a vapor to a liquid phase or a solid phase without anything solid to precipitate onto. So you know that like when, for example, dew forms, like forms on your car or on the grass or something like that, it's forming onto a surface, or it forms onto your drink, right? You have a drink, cold drink, on a hot summer day outside. It starts getting covered with condensation beads, right? It's because everything's condensing onto that solid surface, okay? So it needs to have some kind of solid surface to condense onto. So those things that it condenses onto are actually called condensation nuclei. Basically, these things are like aerosols, right? They're solid particles that are floating in the air, like dust, pollution, smoke, sea salt, etc., etc., etc. Okay? Sometimes they actually do this cloud seeding. So if there's like a drought or something, sometimes like in the Great Plains, they'll do cloud seeding. They'll drop aerosols, and it gives something for some solid particles for condensation to actually form onto, so that you can actually get rain and condensation. Okay. So anyway, moving on to clouds. I'm sure that you know a little bit about clouds from elementary school and middle school and high school, etc. But cirrus clouds are this very high clouds. Okay, so these like 20,000 feet high. The alto clouds are kind of mid-level, between 20,000 and 6,500, and anything below 6,500 we call strato. Okay, stratus, stratocumulus, nimbostratus, etc., etc., etc. Okay, very high clouds like this, cirrus clouds, are usually pretty wispy and thin, and the reason that they're wispy and thin is they're made of ice crystals, and water vapor is very scarce at that altitude, right? Because the air is very cold, it can't hold very much water vapor. Okay, remember how the amount of water vapor that air can hold goes down with temperature. So anyway, alto clouds, stratus clouds, these are the kind of thing that you might get on an overcast day. They're stratus clouds, okay? Nimbostratus clouds are what you get when you get like a warm front coming in and you get stable air, and it's kind of a rainy, cloudy day, right? Whereas cumulus clouds are clouds that form from unstable air. Okay, so these are the thunderheads, right? Highly unstable, and you get especially cumulonimbus. These are, if you hear nimbus, that means rain, it refers to rain. Nimbus really just means cloud, but Latin for cloud, but nimbostratus, for example, is a rainy stratus cloud. Cumulonimbus is a raining cumulus cloud. So basically a thunderstorm cloud, okay, a thunderhead. So number 20 says, what kind of clouds do you associate with these different phenomena? Thunder, hail, lightning, all those come from cumulonimbus, okay? Whereas light drizzly precipitation is going to come from something like this, nimbostratus, okay? I did want to talk a little bit the difference between condensation and precipitation. So when you get precipitation, there's a difference between condensation and precipitation. So clouds, for example, again, they are liquid water droplets. they are liquid water droplets. You're literally seeing liquid H2O water. It's just that those droplets are so small, they cannot overcome the force of air resistance to fall to the ground. They have to get big enough to collect and coalesce and get a big enough droplet to actually overcome air resistance and fall to the ground as water, okay, or snow. All right. By the way, rainiest place on Earth is actually in northern India, Masirnam. I hope I said that right. It's actually at the base foothills of the Himalayas. Gets an amazing 428 inches on average per year of rain. Just to give you some perspective, here in Corpus Christi, we get something like 33 inches is average for us. Okay, so 38 inches is average for America. This place is getting 420, is almost more than 10 times that. If we have a rainy year in Corpus Christi, we get maybe like 45 inches. Okay, so just give you some perspective. There's Aomori City in Japan. So it has it's actually the snowiest place in the world. Isn't that weird? Would you ever guess Japan's the snowiest place in the world? So anyway, difference between condensation and precipitation. So both snow and rain are considered precipitation. It's basically when you have H2O falling to the ground, right? And can either be a solid or a liquid. So there's a lot of different kinds of precipitation. Actually, from your reading, I wanted you to read about some of the different kinds of precipitation, because I go on a pretty long time in this lecture, and I can't hit everything, but I do want you to look up, right, in your book, the different types of precipitation, this time specifically about freezing rain. So that's number 23, okay? I do also want to talk about two common processes to form precipitation. So there's actually two major processes. There's coalescence of cloud droplets, which is called collision and coalescence. That's when two smaller droplets collide and form a larger droplet. That is maybe the most obvious way to make a larger droplet of water. However, it's actually a relatively rare process in mid-latitudes. It's very common in the tropics where there's higher humidity, specific humidity generally speaking, but it's pretty rare here at mid-latitudes. Whereas formation of ice crystals, which is alternatively called the Beer-Geron process, is actually the dominant process for forming precipitation here at the mid-latitudes. So that means outside of north of the tropics. This happens when you get ice crystals forming through deposition, right, through water vapor going directly to the ice crystal phase. And you get formation of ice crystals till they get large enough to actually overcome air resistance and drop to the ground. And usually what happens is here in kind of a relatively warmer place like Corpus, it's going to melt before it actually hits the ground. So the ice crystal will fall as snow, it'll melt, and then it hits the ground. So actually a lot of the water that hits the ground here as rain actually probably starts off as ice or as snow. Okay. So anyway, there are a lot of different types of precipitation: snow, rain, hail, sleet, glaze, freezing rain, lots of different stuff. So I did want you to read about that, a little bit about that in your book. Especially interesting is hail and how hail forms. Forms in very strong updrafts. So what happens is ice crystals start to drop, and they actually get blown back up into the atmosphere. By a rising, right? Remember, there's a lot of vertical movement in thunderstorms, so that rising air lifts the ice back up, and it keeps getting lifted back up, falling, lifted back up, falling, lifted back up, and falling until it gets so big it overcomes the updrafts and falls to the ground. And it can sometimes be, like golf ball sized hail and things like that, or bigger. So, anyway, that's the end of the lecture. Hope you enjoyed it, and thank you for listening. I'll see you next time.